why don't we get started? Today we have Xinran Miao from Wisconsin-Madison.
Thank you for this opportunity and thank you for coming. Today I'm going to present my work on robust transfer learning with sensitivity analysis, and this is joint work with Jiwei Zhao and my advisor Han-Sang Kang from the University of Wisconsin-Madison. And let me start with a concrete example that motivates this line of work. We know that every election runs ad campaigns, but the effectiveness of ad campaigns remains controversial. The recent work by Agri et al. Has been trying to answer the question about ad campaign in the 2020 US presidential election. In particular, the question they wanted to answer is, how would online ads against President Trump affect voter turnout in 5 battleground states, Arizona, Michigan, North Carolina, Pennsylvania, and Wisconsin, for the 2020 US presidential election? So they answered this question by running a randomized experiment on nearly 2 million voters 8 months ahead of the election. Voters were randomized into the treatment or control groups. The treatment group received an average of more than 700 ads against Trump through social media like Instagram. So here's an example of the ad, which says that this former Trump voter would not vote for him again in 2020 because of his poor handling of the COVID. And the control group did not receive such ads. So their outcome of interest is a binary variable indicating whether or not a voter has voted in 2020. So 1 for voted and 0 for not voted. Just wanted to remind you that this is whether they voted but not who they have voted for. So their effect of interest is the average treatment effect, or ATE, which is the difference in voter turnout between the treatment and control groups, and it turned out to be insignificant. So this means that running this large-scale ad campaign on nearly 2 million voters does not change voter turnout on average. What has really caught our attention and motivated this work is a quote from their paper, in which they said, one reasonable question is how well our findings would generalize to other electoral contexts. And we saw this right before the 2024 election, and back then the natural question to ask was, how would online ads against Trump affect voter turnout in 2024? Of course, to answer this question, the ideal approach would be to run another experiment in 2024. However, running ad campaigns can be extremely expensive. The particular experiment by Agri et al. Has been costing nearly $9 million. So what we're going to propose is a less than ideal approach, but it's much cheaper and faster, using the ideas from transfer learning. So here's a simplified data structure to illustrate the motivation before we getting into more details. So we have the 2020 voters collected by Agri et al.'s experiment, in which they knew the voter demographics like age, gender, and party, and they knew whether they have voted in 2020. And what we care about is the 2024 voters, which in red here, where we also observed the voter demographics like age or gender, but we didn't know whether they have voted in 2024. So the question is really to transfer learning from this top panel onto this red panel based on some assumptions. So a key assumption that enables this kind of transfer learning in this context means that similar voters in terms of the voter demographics in 2024 and 2020 should have the same probability of voting. And unfortunately, this assumption is very likely to be violated due to the many differences potentially happen in the electoral context. So for example, we knew that in 2020, people cared a lot of COVID, but in 2024, there were many other concerns, including perhaps the very surprising fact that Biden has dropped out. So before I talk about how we tackle this particular question, let me give you a bigger picture on the questions I care about, which in fact turns out that many tasks in data science are instances of such generalization of transfer learning, in which the data structure can be summarized as follows. So we have 2 different populations, P and Q, and 2 different types of random variables, X and O, where I'm calling this population P as the source population, where we observe X, usually some baseline variable, and O, usually some outcome variable. And in the target population Q, we only observe X. For example, in the election example, the source population P was the 2020 voters from Agri et al.'s experiment, in which they have collected X and also whether they have voted, which is O. And in the target population that we cared about, this was the 2024 voters, in which we only know their X. So just a bit of notation. Here I use P and Q to denote the 2 different populations, and then use subscript under P or Q to denote the distribution induced by the corresponding random variables. So for example, this POX represents the joint distribution of O and X in the source population, and this QX represents the marginal distribution of X in the target population. So our interest is to learn something about the target population, and I'm going to denote this feature we wanted to learn about the target population as psi, and we call it a target functional or target estimand. Basically, it's a functional of the target distribution, where again, notation-wise, this QOX represents the joint distribution of O and X in the target population. And in this talk, I'm going to assume this is a real functional, but if you have questions, I can talk a bit more on vector-based functionals. So here are some examples. The most widely used example is perhaps the mean functional, which the psi I care about is simply taking the expectation of O in the target population. And again, notation-wise, I'm going to use this subgroup and the E to denote the distribution that this expectation is taken over. And a bit more general, you might be interested in parameters defined in Z estimation, in which the psi is defined as the solution to this equation of expectation of x equals to 0 with some pre-specified s, which can be the score function. And as I said at the beginning, in order to learn about this target functional or target estimand, and to use the information from the source, we need some assumptions. And a key assumption that is widely used in this line of literature is the so-called conditional externability assumption. This assumption basically says that the conditional distribution of O given X should be identical between the target and the source population. So just a side note here, well, this talk will be focusing on the context of generalization transfer learning. You might be noticing that this type of assumptions is also widely considered in different areas, including considering the no American founding and also missing at random in causal inference and missing data. But for the sake of this talk, I'm going to focus on generalization. And we can talk a bit more on how to use this in other areas if we have time. However, this assumption concerns unobserved data and cannot be tested from empirically. And like I said in the beginning, it is often violated in practice, not only in the election example that I'm considering, but also documented in the literature. So in this talk, we are going to focus on this type of question by considering robust generalization or transfer learning when the conditional externability is violated or highly implausible. And the tool we are going to use is sensitivity analysis, which is an important tool in causal inference and missing data. So this particular talk would be divided into two parts. The first part, we will focus on more on the analysis or the inference part, which we answer the question, how can we analyze psi if this assumption is violated? And the second part of this talk will be stepping back and be more conceptual. We will think about which design is less sensitive when there exists some violation of the assumption. And here by design, I mean two very specific aspects. The first aspect is that given data, then which estimand, say mean or median, would change the least when conditional externability is violated. And secondly, alternatively, given an estimand psi, then which data set, say source or target data sets, would lead to the smallest change in the estimand when the conditional externability is violated. So before I move on to the first part, do you have any questions?
Sorry, this last part, which source data leads to the smallest change? What does that mean?
But I will hold this question and then you will it will become clearer in the second part. Yeah, thank you for asking. Okay, so let's move on to the first part. So recall that the empirical question we are interested in is how would online ads against President Trump affect voter turnout in 2024? And the particular state we are interested in, Pennsylvania or PA, which is an important swing state in the US presidential election. And our source data P consists of 2020 voters from Agret et al.'s experiment in which we observe X, A, and Y, where X is the voter demographics, including age, gender, party, and voting history. A is a treatment, which is binary, where A equals to 1 means receiving ads against Trump through social media, and A equals 0 means not. Our outcome variable Y is a binary variable, and here we are going to assume suit Y in the sense that the observed outcome is one of the two potential outcomes. If A equals to 1, then the Y equals to Y1, meaning the potential outcome had a voter been randomized into the treatment group. And then when A equals to 0, then Y equals to Y0, meaning the potential outcome had the voter being in the control group. So throughout this part of talk, I'm going to assume strong ignorability in the source population in the sense that first, this treatment is sufficiently randomized, and second, the propensity of getting into the treatment is between 0 and 1, and these are satisfied by the design of Agret et al.'s experiment. And the target population that we're interested in is the 2024 PA or Pennsylvania voters, where we only observe X. Just a bit of the sorry?
Oh, sorry. No, actually, I was going to ask the Untitled analysis, but you're about to cover it. Go ahead.
Oh, yeah, sure. So this is an expanded data table where we have the source data that we observe X, A, and Y, and then Y is one realization of one of the two potential outcomes. And then we have the target data, we only observe X. So what we really care about is the difference between this Y1 and Y0 on this red part, which is the 2024 voters. And in notation, this would be the expectation Y1 minus the expectation Y0, which is the ad effect for 2024.
Sorry, so what does it mean for being exposed to an ad?
Oh yeah, so this was the initial. No, I can show you. No, it's fine. So yeah, so the treatment that they did an experiment where this treatment was to receive ad on social media like this. For example, Instagram, in which these voters were exposed to this short story or video about an anti-Trump ad.
Okay, and this was randomized?
Yeah, this was randomized, conditional on some part of X, and this was done in 2020. And the question we care about is how would this treatment affect voters in 2024? So the empirical question we have is would this ad against Trump remain ineffective in 2024? They don't receive any ads from this experiment. It doesn't mean that they don't receive ads from other sources, but this experimental-wise, they are not receiving such ads.
So why do we think this might have an effect in 2024?
So you would assume that a similar ad campaign happens in 2024, and that exposure, how would that exposure affect? It's not like the same experiment that lasts from 2020 to 2024, but instead you think of how would a similar treatment in 2024 affect voters in 2024, meaning
you would think maybe the X distribution somehow, the demographics shifted?
Yes, and maybe the electoral context has shifted, and then the probability of voting.
You can't really
Is that in the covariates?
no data.
But is that in the covariates that you say the context shifted?
Some can be measured, some cannot be measured. So it depends on your data. So in our case, what can be measured is the shifts in race, gender, age, and part of the voting history. But what cannot be measured are rest of the potential unmeasured confounding.
So the treatment for the target population is not the treatment in the source population. There's also, how do you define the treatment for the target population?
That's a very good point.
Is that part of O or is that part of X? Or is it neither?
Oh, it's part of A actually. So oops. So I'm supposing that there is another ad campaign in 2024, then how would that ad campaign affect voter turnout among the 2024 voters? So because the takeaway of the 2020 experiment is that running this ad campaign will not change voter turnout. And then the question is that would this type of conclusion remains the same if this has been redone in 2024?
So it's part of the O. I thought O was like the stuff that's not measured in the target population.
Yes, you can. Yeah, that's part of the O. So what we are going to consider is always the potential outcome, and what we are going to consider is to focus on the expectation of one potential outcome in the target population to simplify the notation. So yes.
But the assumption is that the nature of the ad is not important. It's just you get the ad or not. While in 2020 it was an ad about COVID, and now it's going to be an ad about Iran or something.
I see the point. So there's some concerns on the potential violation of SUTVA in the sense that maybe your treatment is not very well defined in 2024. And that's a fair point. I would say that in the current version, we don't really have a good answer to that, except for we consider similar mechanism that happens. But we will update our archive version very soon to update the data analysis in order to focus instead on another state in 2020 to avoid this issue of potential violation to the treatment consistency. Yeah, but for now, just think about there's another ad campaign in 2024, and it is comparable with 2020, and we wanted to know whether that effect can be significant or not. Right. So yes, as mentioned here, I'm going to simplify this data structure a little bit just to simplify the notation where I'm going to take this O to be Y1, and then we are going to focus on the expectation of O in a target population. This would be my target estimate set or target functional. So this is a simplified data table. And in order to learn about psi, we will need to make assumptions, as I stated. And the usual assumptions people make in this literature is the A1, A2 assumptions. The first assumption, A1, is called overlap or positivity. It says that the support of Qx should be within the support of Px, which basically says that you cannot extrapolate beyond the covariate space from the source population. And the second assumption, which is the critical assumption in this talk, A2 is the conditional extendability, which says that the conditional distribution of O given X should be identical between the source and the target population. So under these two assumptions, the psi can be identified using the Taylor properties of expectations by, in the case when we have this expectation of O as our target functional, we can simply conditional X in the inner expectation, and then replace this conditional expectation of the target with the conditional expectation of the source, which then can be identified from data. And these two assumptions are very widely adopted in this literature, especially the literature of transportability and generalizability of causal inference. It does allow for the so-called covariance shift in the sense that the distribution of X does not need to be the same between the two populations. But of course, it does not allow for the difference in conditional distributions in the sense that we need X to explain away all the differences between these two years of elections. So the key question we wanted to ask is, what if A2 or conditional extendability does not hold? And we knew that in causal inference, a standard approach to answer this type of question would be using sensitivity analysis. So instead of directly assuming the assumptions and perform analysis, a sensitivity analysis asks for a slightly different question. So the question being asked is, how will my analysis of psi change when A2 is violated? And the particular model we are going to use is the exponential tuning model for sensitivity analysis. So we will be introducing this parameter gamma called the sensitivity parameter, which is a tool for us to quantify the violation of the assumption A2. In particular, I'm going to denote this Q gamma, where to denote that this is the corresponding target conditional distribution when there's a gamma violation to the assumption. And the particular form of violation is in this form, where this F is the conditional densities. So the numerator is the conditional density of O given X in the target population. And the denominator is the conditional density of O given X in the source population. And we assume that this density ratio is proportional to exponential gamma O. So this is saying that if gamma equals to 0, then the right-hand side is 1, and it means the two densities are equal. This returns to the case where A2 holds, which is the case where conditional extendability holds. And notation-wise, this means that we use this Q superscript gamma, where recall that this zero is the place where gamma represents gamma's value, then this means that Q0 equals to P. And when gamma is not 0, in general, this would means a violation of the assumption. Just to be a bit more concrete, when O is binary, like in our case, O is voted or not, and the treatment, then gamma would be measuring this type of violation in an odds ratio scale, in the sense that the odds ratio of voting between the target population and the source population is exponential gamma. Sorry?
I just wonder if this implicit Sutva violation about the nature of the exposure could be considered part of this exchangeability assumption.
I see. That could be. I have never thought of it, but in theory, this could capture the potential differences in the. So if you think of Sutva as part of the difference in the change in this distribution, then this could be. But
one version of Sutva in the 2020 data.
That holds, yes. So, right. But we kind of need this O to be well defined. It needs to be Y1. So it's. You can think of it as a violation you can think of this as also incorporating the violation of Sutva, but I can still see some remaining concerns, but thank you for bringing that up.
Sorry to dwell on the Sutva, because it sounds like it's irrelevant, because if I forget about the observed data, it seems, because that column that you had about A, once you make exchangeability assumption within, or the randomization assumption within the source population, then you're just working with a counterfactual y1.
Yes.
So it's just y1 and x. You want to project what y1 would have been in this new population. So there is no observed y.
That's true. So in this literature, what we really are transporting is the counterfactors instead of the observed values. But whether the counterfactors are well defined is part of the question, because how do you think about running this particular experiment in 2024? Because the ad contents can change.
But you can think of an experiment where the ad content is exactly the same, because there is no data.
You could think of, yeah, that could be thought of, and you can think of this as the intention to treat that in that aspect, yes. So yeah, thank you.
But would that make a violation of A2 worse? Because probably the context, you keep saying that the context matters. So if you imagine keeping the ad the same, the context is going to be more appreciably different, isn't it? So you almost want to think of the ad as having changed so that your A2 violation isn't as serious. So
I see your point.
the context will matter less if you change your ad optimally. So if COVID was the thing that mattered most in 2020 and Iran is the thing that matters most in 2024, then you almost want to imagine that you've changed it. Otherwise, your violation of A2 is catastrophic.
And your estimate is sort of not telling you about what you actually care to learn about, right?
Right.
Thank you.
Yes, that's more important.
Should we just treat it as a different state in 2020?
Yeah, you could treat, yeah, that would make the conceptually easier. Yeah, but thank you for the discussions. That's very helpful. Right, so if exponential gamma is 1.05, then in this context, this would mean that for a voter who received ads against Trump, the odds of voting in 2024 or the odds of voting in another state is 1.05 times the odds of voting in 2020, which is the explanation in this case. And I just wanted to remind you that the purpose of doing sensitivity analysis is not to estimate this parameter gamma, but instead using this gamma as a tool to quantify the violation and see what happens if there is a violation. And before we move on to how to use it, let's take a moment to think about why we use it. Of course, there are many methods in sensitivity analysis, and this particular method has been proposed in the context of missing data by Robbins and his co-authors, and used widely in different areas, including measure confounding and also transportability and generalizability. So there are many reasons people go for it. The particular reasons we are using it is the twofolds. The first is that it makes the inference of psi tractable in terms of asymptotic normality. And the second is what I wanted to stress is the new insights we have on the robust designs, which will be the second part of this talk. So there are documented pros and cons, and I'm not going to talk into details. And the punchline here is that in some sense, most sensitivity models are wrong because they really concern on observed data. But like these authors and like the two parts of this talk, hopefully you will be convinced that this particular model is useful. So under the assumption A1, which is the overlap assumption, as well as the sensitivity model, then we're going to show how we identify the target parameter. Now, again, I'm going to use Q gamma on the joint distribution to denote the target distribution induced from the sensitivity model. And then heuristically, you can think of for any functional psi, we can identify it by decomposing this joint distribution with this conditional distribution induced from the sensitivity model, as well as the marginal distribution of Qx. And recall that in the specific context, where my O is y1, which is a binary variable, and my psi is the expectation of O in the target population, then we can identify it in this lemma, where here this mu x is the conditional mean functional of y given x on the treatment group, which is basically the counterfactual conditional mean. And then when gamma equals to 0, this would return back to the previous case, where identification is just the expectation of the mu x on the target population. And when gamma is not 0, this identification follows by replacing this inner term with the exponential tilted version of this mu x, respecting the violation of the assumption. And after we identify this psi functional, the next step is to do estimation. And I'm going to talk about two different estimation tools and discuss briefly on their differences. So the simpler approach is to directly motivate from identification. Thereby, we may have a plug-in estimator in which we first estimate this mu function using any regression function that you like, and then denote their estimate as mu hat. So after that, we can average this exponentially tilted mu hat among the target samples, where here this average taken over the IID samples from the target data. And then we can construct confidence intervals, or CI, with a two-sample non-parametric bootstrap, in which, under this case, we sample the source and target data individually. And then we can show that if the model is correct, then this estimator is consistent, asymptotically normal, and then this provides a valid confidence interval as well as the resulting p-value.
So how is it estimated?
I didn't talk in the slides, but it basically any regression function that
Parametric or not?
in this part, it needs to be parametric. And in our data, because x is discrete, this really doesn't matter. You just take the average of everything. Yes, yes. But if you are caring about the model specification, then you may be thinking about another type of estimators, which is having rising popularity based on the efficient influence functions, or EIFs. So there are many reasons people may go for an EF-based estimator, and one notable one is that it has the so-called doubly robust rates in relaxing some of the conditions for the nuisance functions estimation. And if you're not familiar with this, I'm going to briefly talk about what does it mean by doubly robust rate in this rest of this slide. So recall that, consider the case where A2 holds, where gamma equals to 0. So it turned out that the EF-based estimator, in this case, would involve three nuisance functions: mu, which is the outcome regression function; pi x is the propensity score in the source group; and the omega x is a weighting function between the source and target. So you can just think of this pi and omega as two different weighting functions.
So, sorry, I think you went too fast when you defined mu x. Is it in the regression function in the source group?
Yes, it is a regression function in the source group.
Same as in the target population.
Under conditional extendability, it is the same.
It is, but you're doing the general case for gamma.
Oh, yes. So yeah, in this case, I'm just trying to give an example of what doubly robust rates means. So this would be like a review type if you are familiar with this. It really doesn't matter what it means. I just wanted to show that it has three nuisance functions, but in this particular context, omega is the density ratio between the covariates in the target and source population. And you can think of it as a weighting function in order to reweigh the source samples to match the covariate distribution in the target. But again, it doesn't matter if you don't really know what these notation means, just these are three different nuisance functions that appear in the EF-based estimator.
Why isn't that defined by pi and marginal build? Isn't omega x by base? Can't you recover it from the odds of pi and the marginal?
It's the transfer. No, pi is between A and X.
Pi is the propensity score, so on the source population. So pi x serves as the weighting between the treatment group and the entire source population, and then omega x serves as the weighting between the source population and the target population. Okay, and then in this case, then it turns out that the EF-based estimator would be asymptotically normal and semi-parametric efficient if these two conditions on the three nuisance functions hold. And the key message here is that instead of the need to having one of the nuisance estimators to achieve sufficiently fast rate, we only need the product of two different nuisance functions, the rate of two different nuisance functions estimation to achieve a certain rate. And that is why the name doubly robust coming from, meaning that suppose you know the propensity score very well enough, then having a faster rate on the one nuisance function can compensate for the potential slower rate for the other nuisance function. And these are labeled as DR1 and DR2, DR for double robust. And now with this in mind, we wanted to see whether we can construct similar estimators in our context, where again, this formula is not really, I'm not going to talk in detail about this formula, but basically we can have this estimator based on the efficient influence function, which consists of two parts. The first part is the plug-in estimator you have seen before, and the second part is some weighted average on the source population that the form doesn't matter as much, but the key message here is that in order to make this estimator asymptotically normal as desired, you really need three conditions. The DR1 and DR2 are what you have seen before. They are doubly robust conditions. And the third condition is really makes this problem interesting, which is solely on the outcome regression function. And intuitively, this is because the bias that has been incurred in the sensitivity model is partly characterized by this outcome regression function. And this means that this is not doubly robust, so even using this EF-based estimator may not guarantee the usual doubly robust that you may have thought of. So in practice, we recommend using this plug-in estimator just for simplicity and interpretability. And if you are comfortable with estimating estimating other nuisance functions, then you're welcome to use this procedure using cross-fitting and standard ways in the literature. So with any of the estimators, let's see what we got from real data. And the data we are going to focus on is Philadelphia, which is an important county in Pennsylvania. And it turns out that when A2 holds, meaning the gamma equals to 0, then the add effect is insignificant. And when A2 is violated, then under a range of gamma around 0, which in the odds ratio scale is between 0.95 and 1.05, then we maybe get the following result. So suppose now I'm letting gamma equals negative 0.05, we get an add effect, and using any of the estimation procedure, it turns out to be significant negative. And we may switch gamma to different values, and turns out that you may get different results. Some cases it is negative, some cases it is positive, and some cases it's insignificant. So the natural question when we see this kind of table is that which row should I look at? Because they seem to lead to completely different conclusions. And in fact, choosing a proper value of the sensitivity parameter gamma is a long-standing question in the literature of sensitivity analysis. Basically, we always wonder what is a large, small, or plausible value of sensitivity parameter. Of course, if you are a domain expert, you may be able to specify a range, say C, and then estimate the add effect within this range. But in practice, we may not have the luxury to have such domain knowledge, and popular approaches, including benchmarking approaches such that people omit one variable from X and then use that omitted variable to quantify the strength of the violation of the assumption. This have some documented issue in the literature, and what we are going to do is a different approach based on calibration by using a dissimilar partition of the source data. And I'm going to describe this calibrating procedure in the next slide, which is the most challenging slide in this talk, so I will go slowly. The key idea we are going to use is to find the gamma that reflects differences between two 2020 subsets, and use that as a proxy for the differences between 2020 and 2024. Be a bit more specific, we have this source data in 2020, and then we partition it into two different subsets, say S1 and S2. In our data, we use Rust Belt states and Sun Belt states, but essentially these need to be two dissimilar subsets. I'm going to temporarily treat this S2 as the proxy target population, and I try to estimate the ATE on this S2 using two ways. The first way is just to use the RCG data on itself, and we call the corresponding confidence interval, or CI, as the oracle CI. And the second way is by transporting information from S1 into S2 using our transfer learning approach with a range of gamma, and we call the corresponding confidence interval as the transported CI. So we are going to define the plausible range C as the gamma such that these two confidence intervals overlap. So intuitional-wise, this means that these gamma would be correctly representing the differences between S1 and S2, and we use that as a proxy for the differences between 2020 and 2024. So you may have noticed that this is the C that we have does not reflect the true unmeasured differences between the 2 years, because the true differences cannot be measured. And however, this particular approach is very useful to rule out gammas that are too unrealistic. So if a gamma is too large enough that cannot explain the difference between S1 and S2, then we consider it as implausible and then rule out such possibilities.
So why do you think the difference between 2020 and 2024 has anything to do with the difference between the different states in 2020?
So basically, we're trying to, say, bound the difference in a way that we feel plausible. And the way we chose it this way is to find a partition in the source data that we suppose there is some difference in the unmeasured there are some unmeasured differences between these two subsets, and we use that as a proxy for the potential unmeasured differences from now to the future. And this may not be true, but this is one way of thinking about it, such that you don't go too beyond. You don't set gamma to be too large. That cannot happen in real data.
But these are two different mechanisms for example, like between 2020 and 2024, right? The difference in actual context and all these unmeasured finding we can think of will be very different from the reasons why S1 and S2 are different, right?
Yes, so the mechanisms can be different, but perhaps the range of change can be bounded in a way that is a proxy. And if you have different thoughts of how this could be changed, you could change the way you split these two data sets. But basically, you want some unmeasured differences in between. Say there's a range of unmeasured differences that are plausible, and I'm going to use that range to serve as a proxy for my difference between 2020 and 2024.
And presumably you don't take any information on the direction of gamma from this, right? Because you could switch S1 and S2 and you'd get negative gamma.
Exactly. So what we do in practice is that we do twice, like S1 to S2 and S2 to S1, and then we choose the overlap of the gammas. All right, and let's see how it looks in real data. So this was the result we had, which has a bunch of results under different gammas, and it turned out that using this approach, we'll be able to rule out some possibilities in the sense that the add effect cannot be negative. Of course, this table is just for illustration, but the results are correct from the real data, meaning that if you run an experiment in 2024 and under these plausible range of sensitivity parameters, this ad campaign can only increase the voter turnout in 2024. So this makes sense because Philadelphia is a quite demographic leaning county in Pennsylvania, and seeing ad against Trump could increase the voter turnout in 2024.
Would you mind going back to the sensitivity model? Yeah. So that gamma isn't counting exactly.
So gamma is the odds ratio, exponential gamma is the odds ratio between the turnout in these 2 years.
So O is
Y1.
okay. But you also have
Yes, exactly. So that's why I'm simplifying this. I said the table is a simplification, but
for Y0, this gamma is telling us about how much more or less likely someone is to vote for Trump in 2024 from 2020, correct?
Yes.
But then it's the same gamma for Y1, is that right?
Right, so these are two different gammas, and again, I'm just simplifying the notation, but presumably there's a Y1 and the gamma 1 and Y0 and gamma 0, and then this calibration procedure holds when you can think of this as a two-dimensional object, so I'm doing this. Yes, but that's a good question.
So, but in your results here,
yes, that's why I said this is an illustrative result. So I'm basically only showing one of the gamma, but in fact, these are intervals. I just try to simplify the table here. But the key message here is the same. So basically, after doing calibration with two gammas both within this range, then you rule out the possibility of decreasing turnout where you only have the potential of having an increased turnout in Philadelphia if you consider this range as a plausible range.
but this is for contrast of
Yes, exactly.
But here you're just assuming that they both shift by gamma on the same gamma on the same scale. Okay, I see.
So the table is just showing that, but the results are different gammas. The key message are two different gammas, but I'm just showing it to make the notation simpler. Yeah, that's a good question. Thank you.
And sorry, how do you do the calibration differently for the two gammas?
So the idea is the same, that you just choose the gamma pair, say the two-dimensional pair, and then find this pair such that it transports from S1 to S2 and then S2 to S1.
So do you mean that you take your source RCT and you take the A equals 1 subset and estimate gamma from S1 to S2 there, and then you do the same for the A equals 0?
Yeah, maybe I can show you a picture. So the fact that in reality, what we do is that we have gamma 0 and gamma 1, and both of them are within this small range. And then this would be the result where you choose values on gamma, and then you can get the result using any of the estimation procedure. And then you find the plausible range C, say this range, using the calibration procedure. And finally, you only care about the points that are within this range. Yeah, thank you for the questions. Okay, so this is what we get for Philadelphia, and then we applied it for the other counties as well. In Pennsylvania, where here this is a map of Pennsylvania. Before we apply any sensitivity analysis, when I choose host, then the add effect is insignificant in most of the counties except for this Fulton County. In this Fulton County, the effect can be significant negative, where Fulton is actually the most Republican-leaning county in Pennsylvania, meaning that if there's no unmeasured differences between years, then running an anti-Trump ads can decrease the turnout in the most Republican-leaning county in Pennsylvania. And if we apply this sensitivity analysis with the plausible range by the calibration, then this would be the result. So first, I'm going to point you to this Philadelphia, which we have seen before. It turned out that also in this plot, I only plot the values that can indicate a significant result. So this is the Philadelphia you have seen, in which the ad can significantly increase the turnout. And it turns out that Philadelphia is the only county which may have an increased turnout. In the majority of Pennsylvania, this ad campaign against Trump can only decrease the turnout. And there are some exceptions in which the ad campaign cannot be significant, regardless of how you change gamma within this rule. And for example, Allegheny County is one of them. This is the place where Pittsburgh is located.
So can we intuitively explain why before you do this, the original results were all non-significant, and then after you do this transfer learning and you do this sensitivity analysis, and all of them become significant?
So you can think of it as the sensitivity is introducing a bias into the original, or introducing a change in the value of the original effect. So say the original effect is 0, and then if you assume there could be some unmeasured differences, then you are adding some bias to it. And then the 0 may become 0.05, and maybe this becomes significant.
So significant is just one plausible gamma.
Oh, yes.
No, just one.
Any one possible
Only one.
Yes. So that's what has been said here. So we are only interpreting results for this plot, for the particular gamma that can make a significant result.
You have not run into an issue where you get both significantly positive and negative.
In this particular data, no, but in different data sets, yes. We have other data applications ongoing, and it is possible that they can be sensitive to both directions, and that also makes sense because sometimes you don't get to know whether this is positive or negative. But in this particular data set, we don't run into that issue.
So the interpretation of this right thing is there is a gamma within the range that makes this significant.
Yes, yes. So in practice, if you wanted to have a more quantified version of this, you could find the smallest gamma such that there is a significant result. So that this would be one way of mathematically quantify how sensitive each county would be. But just for the sake of this talk, I'm only showing the case where there exists.
The bias would be towards the null. Is there what do you foresee as being the driving mechanism so that it's significant for a non-zero gamma, but it's not significant for gamma equals 0? Do you have a sense of? Because usually we're worried that the bias is away from the null.
Yeah, so this is quite opposite to the usual sensitivity analysis. Here, when there's no unmeasured confounding, it is null result. And when there is confounding, then you may increase or decrease the add effect.
Do you have a story for the narrative? What's the narrative why you might expect the bias to be in that direction?
So in this data set, we think the sign of the effect is mostly driven by party. Yeah, so but and we have another ongoing data application in which we found that race is also an important factor that affects the direction of the effect. But in this data set, in Pennsylvania, we don't have the race variable, so the most indicating variable is party.
You don't have party here?
Oh, in this part, we have party.
So party is not being captured by gamma. So gamma is capturing something that you haven't measured, and presumably
That's true.
is shifting. And so you don't have race.
No, we don't have race. Yes, no, right. We don't have race in this. So what we are speculating is that. Oops, let me go back to this. So suppose this is potential results under different values of gamma, and you can see that under the center where both gammas are 0, this would be null effect. And then if you change gamma, effectively you are changing your point estimate. And then this would give you different kinds of results, increasing or decreasing, depending on what gamma you choose. But after using this calibration with this plausible range, then what we see from our data is that effectively this rule out some of the, say, the red points on this corner, and then we are only left with these blue dots, which indicates an increase of turnout. And that's what happens in the real data of this particular problem.
Can I just check in all counties, it would be non-significant if you had set gamma equal to 0?
All counties except for Fulton. So
because it could be that the distribution, the change in X could also change the R result, as in could take us from a non-significant to a significant in some direction. It's not not only gamma, but
yes, exactly. So if you think that gamma is not changed and only X changes, then this Fulton is the only county that the effect is significant.
Yes. Yes. No, I see. Yeah.
But 0.04 is, if you do 67 comparisons in there.
Yeah, if you do that, then this would go away. But this is still telling you something because the p-value is still smallest for Fulton, and it really makes sense because this is the most Republican county in Pennsylvania.
So if this really comes from the null, and if you do 67 comparisons, we would expect on average 3 significant.
I see your point, but there could be correlation between different counties in a way that we really don't know what's happening inside. So a proper justification of the, say, multiplicity, and also needs to respect the potential correlations inside, and also this is not a uniform distribution in this case, but we didn't know, we didn't investigate that without further information about this. All right, so I have very limited time. I wanted to get into the second part, which will be brave. And
Which I think is fine. It's very interesting. So I was curious about this result that you have, that you get square bias in mu. And
I see.
I think it's your choice of parameterization. So omega is the likelihood ratio of x.
Yes.
But if you choose the likelihood ratio of x given the baseline value of y, I think you get mixed bias. But I think Jamie, in the original result when they were doing it for missing data, you have an additional complication here, which is you have 2 levels of missingness. The causal one, I don't think that's the problem. I think the issue is in the SFT analysis model, they use a different randomization than you do. They use for omega, you can think of it as the indicator of which population you are, like a propensity score for which population you are, given the covariates, that's the one you're using on the likelihood ratio scale, but they actually use given the covariates and y equals 0.
I see.
And then they get mixed bias.
So does it require y to be binary?
No, just a reference value for y. That's the nuisance parameter, if you will. And it's still variation dependent, but you do get mixed bias with that. So I was curious about whether there's something else going on, or if you tried that at all.
I will try that. I didn't try that. So yeah, it could be. In this case, we are decomposing it in the way that's conditional on the population, but we could try the other decomposition of likelihood you mentioned.
I don't think she's even using the missing data perspective.
Right, but it's the same object. The influence function is exactly the same. If you just forget about the causal story, just focus on the two arms. From that perspective, it's I think it's isomorphic to the Sensei analysis that you cited, the Sharfstein, and there they have a doubly robust estimator, but they use a different parameterization.
Right, because here she used the density ratio, which.
That's what I was saying. Yeah, I think that's why you get the mu squared. Because double robustness, it's the same influence function, but double robustness depends on picking the right parameterization.
Thank you. Yeah, thank you for bringing this. I will look into this. Right. So I will go through the other part real quick. Hope this does not bore you. And so the start of that would be a visual illustration of what we have done. And to think about it conceptually, what we have done before is that we think of gamma on the x-axis, and the midpoint is gamma equals to 0, where the assumption A2 holds. And we are interested in the psi function now, and here I'm going to consider it as a function of gamma, and I plot this in this red curve here. And what people do is to assume gamma equals to 0 and then check out what's the function I'm interested in. And what we just now did was that assume there's a change perturbation around gamma equals to 0, and then we wanted to know how it lies into different values of psi on the y-axis in this red bar here. And now, suppose we have a different function, say psi tilde, and then it may be similar to psi when gamma equals to 0, but it may change with a varying psi with a varying gamma in a different way, in the sense that in this green curve here. So in this time, if I perturb gamma again, then I will result in this smaller interval on the y-axis. So intuitively, this seems to suggest that psi tilde is less sensitive than psi when there is a perturbation of the assumption. And so this goes to the empirical question of which estimand, say mean or median, would be less sensitive when A2 is violated. And of course, perhaps you are not interested in the psi, but you are interested in different data sets, say Q and Q tilde. And then in this case, this would correspond to the question which data set, say Philadelphia and Pittsburgh, would be less sensitive when A2 is violated. So the data set could be the target data set or the source data set and then you will see that in the notation in the next 2 slides. All right, so in order to understand how sensitive my y-axis changes with respect to a small perturbation in the x-axis around the value, a natural tool that we can recall from calculus is the derivative. So that's what we are going for in this part of talk, which we will provide a derivative-based measure of sensitivity that we call it slope. So recall this was our sensitivity model based on this exponential tilting. And we are going to propose slope, which is short for sensitivity to local perturbation from exchangeability. And we define it as the derivative of the psi functional with respect to gamma at gamma equals to 0. So as this name hints, the slope is literally the slope of this tangent line of the psi curve at gamma equals to 0. So as the motivation and this plot shows, the slope naturally is a measure of the sensitivity of a design in the sense that the higher slope in magnitude corresponds to a more drastic change in the estimand when there is local violation of the assumption, and thereby this indicates a higher sensitivity. So this also corresponds to some recommendations in robust statistics in which Huber has mentioned in his book that robustness signifies insensitivity to small deviations from the assumptions, and here we're following similar rules that we consider the sensitivity of small deviations from the A2 assumption. And notation-wise, slope depends on these 2 quantities. The first is Q0, which is the underlying distribution when conditional externability holds, and that is the data set I'm calling in the initial slide. And psi is the functional or estimand that we're interested in. So back to the these comparisons, if you have psi and psi tilde, then naturally you can compute their slope and find that in this case, the slope for psi tilde is smaller, then this is less sensitive. And similarly, maybe you have the same psi but different data sets, say Q and Q tilde, then you can consider the slope that Q tilde has a smaller slope than Q. And I wanted to point to you that slope is a measure of sensitivity at the population level, and that's why I call it a robust designs. And it is agnostic to how psi is estimated, say using EF-based estimator or regression estimator. It does not change the value of slope. So this reflects the high-level conceptual idea that one design can be intrinsically more or less sensitive than another design, irrespective of how the underlying estimation is performed. So of course, in practice, you still need to estimate slope, which I will not cover, but the high-level idea is distinct about the sensitivity of a design and the sensitivity of an estimation procedure. So since I brought the robust statistics at the beginning, I wanted to quickly mention that if you're familiar with this, you might be noticing that slope as a local derivative is similar to another important local derivative in the literature, which is the influence function, IF, which is proposed by Hampel. So basically, the influence function is also a local derivative when there is a small perturbation around the Q0, but the difference of the influence function is that the consideration is on a contamination model, which the original Q0 is contaminated by a direct delta measure at a different point. So it turns out that slope is connected to the influence function not only in this conceptual idea, but also in a more analytical way, in the sense that under regularity conditions, the slope happens to be this form, which the outer expectation is taken over Q0. Basically, the target distribution had conditional extendability holes. And inside this is a product of two terms. The first term is influence function, and the second term is O minus mu x, which mu x is the conditional mean of O given x on the source population, and you can think of it as a residual. So this is saying that the slope is the projection of the influence function onto the residual space, and the intuition behind is that you can think of the influence function as a measure for the sensitivity of this functional psi. And you think of this, the other residual term, as the sensitivity that caused from this sensitivity model. So recall that my sensitivity model is based on exponential tuning, so the derivative is fairly simple in this case. And of course, this does not only provide a general formula, this does not only provide a geometric insight, but also a general formula for slope. And let me quickly implement it in a data in which we consider back the mean functional, which I'm interested in psi mean, and I'm think about just the observed outcome is whether or not the voter has voted, and there's no causal element inside. So the question is, suppose I'm treating one county in Pennsylvania as the source, and I treat the rest of the counties in Pennsylvania as a target, then what would be the county that is the least sensitive, characterized by slope? So the slope for the mean functional in this case turns out to be the expectation of sigma squared x, where sigma squared is the conditional variance of O given x in the source population. And this generally holds whether or not your O is binary or continuous. And here's the result. Again, this is a map of Pennsylvania, and these are values of slope in the color gradients. And what I wanted to mention is that here, Philadelphia has the highest slope, meaning that generalizing from Philadelphia to the rest of the Pennsylvania state would incur the highest level of sensitivity. And this makes sense because, as you might have seen from the previous example, Philadelphia might not be the most representative county you can imagine in Pennsylvania. So this concludes the two parts, and just a bit of comments. There could be extensions and future directions. If we consider P and Q differently, this may indicate insights in other contexts of the conditional extendability assumption. And then we are also interested in extending this derivative-based approach into other sensitivity models, for example, the bound-based models. And with that, just one sentence summary, we're considering sensitivity analysis as a way for robust transfer learning and generalization. And we have archived papers online, and I wanted to thank you for your attention, and thanks to all these colleagues and friends for their valuable feedback. Yeah, that's all. Thank you.
I don't usually comment on data applications, but it seems like data application is a very central part of your paper. So like, I'm having a hard time understanding the utility of transfer learning in the particular data application that you're pursuing. So like people raise the issue of, the definition of the treatment from 2020 to 2024, that's one thing. And then I think you mentioned that you're changing it to be just within 2020, right?
Yes.
But even then, like, the election is, if it's over in one state, it's over in all of the states. So like, there's never a situation in which you'll have Y for some of the states, but not the others. And so like, what is the application of transfer learning in that scenario?
I see. So first is that getting these Ys are very expensive. So in some states it may it's free, in some other states it may cost say $10,000, like in Wisconsin. So there is a cost of obtaining the data in different states, and the cost, and moreover to that, it's really not the cost of having this Y outcomes. It's the cost of running this randomization procedure. That's what really costly, because
Yeah, but you can't run the randomization procedure in the other states because the election is like over. The 2020 election is done. So like you would never think of running that ad campaign anymore for the 2020 election.
right, but so the whole motivation is that suppose this 2020 campaign has been over, then I wanted to know what if I run a new campaign in 2024, and that could inform important directions of the ad effect, and that's why. Yeah, so in
problem, it's like, yeah, I mean, like Trump, if all goes well, Trump is not going to run in 2028.
Yeah, but I see your point. I think there are other variables of interest, is whether a voter has voted early, and that could be also an indicator of the how people wanted to vote. So in that case, yeah, there could be variables that you might be interested to transfer between states in the same year, and you might not getting the access to the voter database across different states. So that could also be reasons, but I see your point of saying that, yeah, if it's on the same year.
Caleb?
So the slope. Oh yes, for the slope. So you have if you wanted to transfer like the contrast, you have two different gammas, right? So can you generalize? Does the slope accommodate multivariate sensitivity parameter?
That's a good question. I think the problem is not about the definition, it's more of the interpretation. So here we are trying to compare slope across different, say, between mean and median, or between different data sets. So basically you just have one value to compare. But when it gets to a vector, say you're taking derivative with respect to a vector, then the problem is that how you're going to think about this vector. Do you specify a norm, or do you, yeah, the question is more on the interpretation side. It's the question that we're not having a very good answer to that.
And then sorry, one last thing. Limbo raised this issue of why does sort of extrapolating from 2020 to 2024 have anything to do with comparing across counties? But like, if you have more historical data, like if you have data from the previous election, then you could, in theory, do that from 2016 to 2020. I mean, I guess you would have a different candidate, but still along parties, you could. That might give you a more.
Yes, and even if you don't have I mean, if you, in your case, what you mentioned, that you kind of need to have two experiments in 2 years and then you compare them, this could also not be that possible. But one way we can think of is that you straight compare the voter turnout without any experimental data coming on, and then use that as the initial range of the sensitivity parameters. And then you just shrink from this initial range to a smaller set of plausible values. So that's also one thing that we can use in our data set, even without two experiments going on. Thank you for bringing that up.
I have two questions. This connection with slope and the influence function, is that general, or Is it just a coincidence in this case?
It is so.
You're kind of taking derivative of the functional, but with respect to different perturbation. So
Yeah, so maybe I can show you a bit of the intuition. So if you think of this, sorry, there might be some typos, but if you think of this as proportional to some function, say row function, that's a bit more general than exponential tuning, then in the end, the result changes into this way, where here it becomes the derivative of rho with respect to gamma, and then minus the conditional expectation of that derivative. So basically, this part is quantifying the effect from this shift, but this is, again, under some density ratio shift. And if you wanted to use other sensitivity models, I only have some very preliminary results that, oops, maybe not here. Sorry, I can, so if you think of other sensitivity models, then if you think of bound-based models, then you kind of need to think of this question differently. If you don't have a Q gamma at a single distribution, but you have a set of gamma, then you need to define it with respect to the bounds of the psi you eventually get from the model, and this could be more complicated.
and very quickly on the data, I thought, one way to look into that original data set was, it's not significant overall, but as you were showing, there's some differences in different counties. And have people looked into the kind of heterogeneous treatment effect of the original? And that feels like it would give more kind of insights about, for example, where to target in 2024 than this kind of.
Yes, so in their original paper, they have thought of the differential effect across the so-called Trump support score, which is a variable in their data set. And the reason we are not after that was because in our Pennsylvania data, we don't have such score. So we cannot compare it in that way. But we do have a subgroup analysis with respect to gender, education, and those are factors that influence the sign of this.
All right. If there are no more questions, let's thank Xinran again.